For those of you who don't know, my name's Clinton Hilliard. I'm the incoming programs director, and so this is my very first time up front here introducing folks, and so you'll see more of me down the road. So who we've got here is our illustrious current president, Mark Evans. Mark's been around a little while, 40-plus year career in engineering. He has a MS in electrical engineering and MS in national strategy from the National War College. He's an ASEP. He's also retired now, right? Is that right? Yeah. But he was a senior executive leading NSA's Enterprise Architecture Systems and Engineering Group, and has been at the forefront of systems engineering for the national security for quite some time. So I'm going to let Mark, welcome, and I'll let you get started.
Thank you, Clint. And I'd like to thank everybody here on this not so cold January evening for attending, and everybody out there in Radio Land. Boy, I'm dating myself there. But hopefully we'll have an interesting talk. And what I will do is give you food for thought and maybe stop midway for questions, and then again stop at the end of the presentation for questions. So without further ado, we will get going. Oh, I did want to comment that I wanted to thank the Chesapeake chapter for inviting me to be a speaker tonight. At first I was very, very honored, and then I realized that this is the slot that they throw to the new president. So I was less impressed with the invitation, but I hope everybody enjoys what I have to say tonight. Here's the outline. We'll start off with a little prediction humor and forecasting. And then I want to get into what I think are 3 existential challenges that are huge, and they actually have the potential to break system engineering as we know and practice it. And this is food for thought, probably also open to argument. Our definition in Incose of an engineered system, it creates a boundary problem with respect to the 3 challenges. And the 3 challenges have no easy boundary, and that really is the greatest challenge, is how do you rope these 3 challenges with some kind of boundary so that you can begin to even dive in and engineer against the problem. And then after I explain that, we'll get into, well, what do we do about it? So, anybody that has worked in technology or is the president of something has historically been cautioned that presidents of organizations, college universities, et cetera, have a really, really lousy track record of making any kind of prediction. So I'm a little bit wary of this talk tonight for that reason, because I know I may be quoted later on, and I know that what I say in the way of forecasting is invariably going to be wrong. Niels Bohr said it best. Prediction is very difficult, especially if it's about the future. And then we have Sir William Preece, who is a British gentleman who believed that the Americans have a need for the telephone, but the British could do very well without the telephone because they had plenty of messenger boys. Then back in 1946, Darrell Zanuck made a prediction that television wouldn't last any longer than 6 months because there was really no market for it and people were going to get tired of staring at a plywood box. One of the all-time favorites is Ken Olsen, the CEO and president of DEC, who still has not lived down his prediction that there really is no reason anyone would want a computer in their home. But wait, there's more. Robert Metcalfe, he predicted the internet would soon go away after a spectacular supernova, and then it would catastrophically collapse. And somebody, maybe not known to everybody, but in the software world, and a pundit, Clifford Stoll, said, And he got some of it right. He said, the truth is no online database will replace your daily newspaper, no CD-ROM can take the place of a competent teacher, and no computer network will change the way that government works. Well, he was reacting to the inundation of information and email. So in that regard, he got it right, but in all his other predictions, wrong, wrong, wrong. But wait, I saved the best for last. Thomas J. Watson, CEO of IBM, said he thinks there's maybe a world market for 5 computers. Now, he was talking, granted, he was talking about supercomputers and really high stuff, but again, he really missed that mark. And Bill Gates, who denies he ever said this, did not say this exactly, but he said something that this summarizes, and 640K ought to be enough for anybody. That quote, whenever he's reminded, is said to really get under Bill Gates' skin. But and the final quote, which is fiction, but it comes out of the well-known 2001 movie about whether or not we can control artificial intelligence. And anybody that's seen that movie knows how badly wrong the whole attempt went when they tried to control Hal, and Hal kind of got out of trouble, or I should say he got out from under supervisory control on the mission. So tonight I want to talk about 3 challenges. The first, artificial intelligence. And when you talk about intelligence, it's almost a point of religion, what intelligence is and how we define it. I'm going to use the definition, a very, very simple definition of intelligence, that it is very simply the ability to process information, either naturally, which is carbon-based, or otherwise, meaning artificial or some other means. And the reason it's being processed is there has to be a reason. Just garbage in, garbage out is not intelligence, but there is an input, process, output, and usually that information gets digested and gets put into some form known as knowledge or wisdom, and it gets applied. So the intelligence involves the ability to apply that knowledge that has been created from a process of information. So that's the definition. Psychologists get to other definitions, and if you talk to a true AI person, they believe that computers and machines eventually are going to duplicate the human ability to compute and to think. And that's still argumentative, although I think that more people are tipped in the direction that machines will duplicate the human capability. The big lament by the AI community is anytime that they come up with a real big score in terms of a capability, engineers and computer scientists are very quick to rip it away from AI, call it an expert system, and point to the fact that it really is an artificial intelligence. It's just an algorithm doing its job on a computer. And this has been going on ever since AI was invented, so that's why they lament it. Another big question is superintelligence a real possibility? And I think yes. I'm in the camp that says yes, but the better question is, what do we do before superintelligence gets here? Superintelligence is really defined as a singularity. So once AI gets so smart that it begins to think for itself, there's going to be a huge burst of activity, and it'll go from AI smart and able to interact with humans to an intelligence that far surpasses any known or conceivable human intelligence on the planet. And at that point, we'll be outstripped, and then the issue is, what do we do? And just in case you missed it on AI, it's AI, the whole AI discipline and the whole AI arena, very, very active. They're producing algorithms at an accelerating rate, and some of the examples like word recognition, playing chess, solving mazes, those are from 20, 30 years ago. Recent technological progress in this area came faster than anybody ever thought of. And you've got new things like neural Turing machines, deep reinforcement learning, Bayesian hyperparameter optimization, grid LSTMs, memory networks, just to name a few. And those of you that are in AI probably familiar with this. Some of you system engineers that don't pay a lot of attention, this is something I think system engineers need to start getting more involved in and need to be more conversant with. And Hollywood hasn't helped this whole thing out because the big fear is that machines are going to take over and dominate the human species. And you've got two good examples here, courtesy of Arnold Schwarzenegger and his attempt to come back from the future. So there are different things like the people that are really fearful of AI and the progress it makes talk about a Robo Apocalypse, which is where we've got all these robots running around. There's certainly a lot of science fiction stories, and there's some movies that show that. And in those movies, Asimov's 3 laws of robotics are looking a lot less like science fiction and more like the only hope for our survival of the species, except there's a problem with the 3 laws of robotics, and I'll get to that later. One of the issues here is motivation. Why would a robot seek power? If robots are truly logical and they're emotionless, they're more on the order of Mr. Spock in Star Wars, and they make rational decisions. They do so with reason. They don't really have any kind of emotional reason to motivate them towards world domination. So that could be one of the aspects. Another thing is the control aspect. Is a robot going to really have a survival urge? Will it act in its own best interest to continue to perpetuate itself? That's something that is often debated. And again, you're in an area of philosophy and not in an area of engineering or logic. We need to caution against anthropomorphizing. I can't say that word, but you can't basically turn a machine into a human with all the human motivations and emotions. And in fact, that is the whole problem, is if you give an AI capabilities that a human has, do you also give it the motivations? Or is the science yet smart enough to know how to give a machine the motivation? And bottom line, carbon intelligence and silicon intelligence are not the same thing. They're pretty widely separated at this point. Why humans may have an edge is, well, number one, the 7 deadly sins. Those of you that know the 7 deadly sins can realize that it's pretty hard to take those sins and program them into a machine. Why would a machine have lust or greed or gluttony or anger for that reason? Why would a machine know envy? So this could be a saving grace. Our ability to reason and extract ourselves out of a strange loop, that in itself could be the saving grace for a human intelligence. The other mathematical reason, Gödel's incompleteness theorem, which has been proven, and any axiomatic logic system that you can come up with breaks in the sense that you can create a statement that's perfectly legal within that logic system that can't be proven with the logic system. You have to go outside of the logic system to prove the statement. So regardless of how intelligent a superintelligence becomes, if you can hang your hope on Gödel's incompleteness theorem, there's got to be a way to break it. There's got to be a way to get inside of it and control it. So those are some of the advantages. And the humans, the machines, if they're going to take over, they just really need a motivation. And that motivation probably isn't there if it is designed with a noble intent. However, you get a human that is evil in the loop, and it could be possible that you see evil robot armies or evil or should say bad actors that are actually AI. So these are all the debates. This particular book has that whole discussion, and it does a great job of taking some of the most notable people in the field and sampling their opinion. And the book is about 50-50, pro-con, on whether or not machines are going to have an edge or whether humans will always keep an edge. So there are a lot of examples where AI can seriously go wrong, and like any kind of technology, if technology has a runaway, it's always the unforeseen consequences of technology going awry. A lot of great movies out there that really enforce this principle. The Robo Apocalypse most likely isn't going to occur by itself. Somebody's got to have the concept of evil that they teach a machine. But there are a lot of bad actors on the planet, and there are a lot of people working this in areas that we're not even aware of. So to say that it isn't the case that we won't have a killer robot army arms race is really hard to determine at this point, and I think that's a threat. The Steven Pinker is a well-known cognitive scientist, and he's head of psychology up at Harvard. He's written a lot of books, and in many of his books he points out that machines don't really have emotions, and in the cognitive sense of an algorithm that can think, it doesn't really have the ability to extract itself from a strange loop. Now that opinion might be somewhat dated based on some of the research, because there are stop points now that AI is putting into algorithms where the algorithm actually can extract itself and is intelligent enough to take another path in its decision making. So when we cope with a superintelligence, this right here is a great book written by Nick Bostrom, and it's the Door Prize tonight. So it's a really interesting read. It's a hard read. It's something that once you read it, you probably want to come back to it several different times. But in the book, what Nick Bostrom identifies is there's two big issues still open that are what we can use as really a judgment as to where we're going to go in a design process. This is how you judge the merit of whether it's good or bad, and that is the control method and the control problem and the value loading problem. Those are the two problems. So the control method has to do with, is there a way that before this intelligence explodes into a superintelligence, humans can get in so that we seed the intelligence with enough values and enough motivation so that it will want to interface with humans and want to do good things for humans. And that wanting to do a good thing and being motivated in what we term socially acceptable and what we want it to do is the value loading problem. So we teach the machine how to acquire a value and how to use that value in everything it does. Kind of like Asimov's 3 laws of robotics, but much, much more complicated and a lot more comprehensive and cohesive than just Asimov's 3 laws. So when we get here, does this really mean that SEs need to become experts in AI? My answer is yes. I think all system engineers need to be very knowledgeable about AI. They need to know how to incorporate it into any kind of design and at least interface with it because it's already out there. And you hear more and more about it, all the way from driverless vehicles, unmanned combat air vehicles, refrigerators that can talk and tell you when they need a new water filter. There's all types of AI that is already being seeded out into products. Here's the control methods for a superintelligence. And the top 4, the capability control methods, have to do with how you actually control an intelligence if you're able to seed it before that intelligence explodes into a superintelligence. So they're not in any particular prioritized order because you could use combinations of all of them. For instance, the boxing method is somewhat limiting and could be self-defeating, but in a boxing method, you severely restrict what the intelligence can do and you bound it in a way that it can't go beyond that boundary. One example would be the first law, Asimov's first law of robotics. First, do no harm to humans. Well, the problem with that, you can quickly see it gets to be, well, what do you mean by harm? And am I going to optimize the amount of harm done to a human so that there's only some harm, or is there no harm? And if it's absolute zero tolerance for any harm to a human, the next question is, well, can you say something to a human that will hurt its feelings, because that could be interpreted as doing harm? So you quickly put constraints on a machine that starts to put it into an endless loop where it can never really do anything because of its concern to do harm to the human. One example of why the boxing method has got its issues. Incentive methods, they again work for humans, but on a machine, if you tell the machine that you're going to give it a different frequency of power, or you're going to give it more kilowatts in a week, does that incentivize it to do anything? The question's unknown how that works. So some of these are methods that would keep an intelligence from exploding, but maybe not help it get there. When you get down to motivational selection methods, those are the area that helps with the value loading problem. And there's some more hope that research into those areas are going to actually produce results, such as direct specification, where you tell the machine what it is you want them to do. It's kind of task-oriented, and you give it some specification where it follows a set of rules, and you throw a reward in the path so that once it completes the set of rules, it can go on to another task. One of the issues there is with machines, particularly robots, once you give them the ability to have a value system and some motivation, are they going to want to offload the mundane tasks that humans do? And that's another one of the big problems, is that if you truly achieve humanness in a machine, or human-like qualities in a machine, then you're going to have to deal with the same kinds of lack of motivation or laziness on the part of the machine. So the better we get at taking machine nature and modeling it in a way so that it approaches human nature, then we get into an even bigger issue, because we can't really model human nature. We don't really know what the human nature is, or how it gets modeled down at a primitive level. So, as I said, the traditional approach to controlling an AI for the past 50 years has been Asimov's 3 laws of robotics. Well, this is, for our species, this is kind of an embarrassment that the 3 laws remain state-of-the-art for over half a century, because there's some really, really big problems, and I've already alluded to some of them. In fact, from some of Asimov's later writings, it was clear to people that Asimov knew the problem that was embedded in the 3 laws, and he actually left the problem in the 3 laws as a loophole so that he could write other books and come up with scenarios where a robot could actually get outside that 3 systems of laws. So I've already talked really about the harm, but when you start digging down, it's reminiscent of what Bertrand Russell said, and he said, the deeper you delve for understanding into a concept and you get down to the primitive of the idea, the more you learn and find out that you really don't understand it. And that is the whole problem with our Western science, how we take things and decompose it all the way down to the primitive, down to the root level. And when we get down there, we can't figure out how those primitives actually build the system back up. That's part of linear science, and it's one of the challenges to system engineering today, where we are trying to take more of a holistic viewpoint of the whole thing. So here's some of the risk and rewards to a superintelligence, and you can see each one of these different tasks that it does. What I've done is taken the skill set and show you where that skill set is a good thing and it's green. If it's a questionable thing, I did it yellow. And the strategic relevance for some of these are pretty much in the red area. And the reason is because the whole task can be subverted and it can be put to the end of an evil means. And that's where, for instance, technology research, if we had a super intelligence, it would be great for humanity because we could go out, research every idea, we could create relationships that people have never even dreamed of, we could expand our design and modeling techniques, but what could also happen is a creation of a powerful military force adverse to our own wishes. We can have surveillance systems all over the planet that we don't want. And for instance, I recently learned that people that have some of the more modernized CPAP machines, the time when they go to sleep, use the machine, and the time when they wake up and the duration and all that automatically gets linked to the home base, and those people have all the information on that patient or that person using a device unknown to the person. There's cell phone links right out of the machine to the home base where the machine comes from, which is talk about surveillance. You know, it's people know where you are and what you're doing every minute of your life. So the next, so that's the big threat with AI, and the next threat is fifth generation communications. Now, if you believe the marketing hype, 5G is a great thing. We're going to have ubiquitous communications everywhere we look, and everything is going to be connected in an Internet of Things. And this is goodness, right? So when you drive down the street, your cell phone will tell you whose ice maker in a refrigerator is working and whether or not the filter in that refrigerator is good and if their furnace needs a change of an air filter. All kinds of information that can get popped right to your cell phone that you probably don't need. The main technological enablers to this are cloud computing and software-defined networking and network functional virtualization, and which is all good technical buzzwords, meaning we're going to do it all in software. It's going to be highly portable, going to be very, very virtual, and everybody can communicate with everybody worldwide, globally, that they want to. However, there's some really pressing security issues with this. If you look at some of these issues, the network is moving away from centralized hardware-based switching. It's all going to be in virtual servers in software. That's a real problem. Anybody that can get into that server is basically got control not only of one or two communications, but the entire network. 5G will further complicate cyber vulnerability by taking all the higher level functions of that network and putting them in software. And finally, what you're going to do is you're going to connect billions and billions of devices to this network that are going to be easily hackable by bad actors. So this is something that, before we race China to Huawei in particular, to who can put up the 5G network that becomes a world standard first, that race to the bottom is effectively a race to the bottom. We need to take a really serious look at how we secure that. So does all this mean that SEs need to become network and cybersecurity experts? My answer again here is yes. It's just one more skill that we got to load on SEs and make sure they're very familiar with it. So here's a good high-level architecture diagram that shows some of these security threats just at a high level. Got flash network traffic. User plane integrity is not secured. There's no cryptographic integrity at that user data plane level in 5G. Anytime you roam with the security of 5G, because it's all in software, you've got crypto security that may or may not be roaming with the channel that roams through the system. Denial of service is going to be really, really easy to do and to attack 5G. You'll have signaling storms all over 5G from bad actors that at will be able to generate a signaling storm and a denial of service. So digging around in the literature, this is one of the reports that was done by the Council of Economic Advisors out of the White House. And what they found in 2016 alone, the cost to the US economy of cyber threats to the global connectivity is as high as $109 billion in 1 year. That's just enormous, and what a drain on our GDP. It's amazing that that much money is lost from cyber attacks and from all the effort that it creates. So a cyber attack in reality could be against critical infrastructure or against the network, could be very highly damaging. One of the big problems we have right now in cyberspace is no nation has stepped up to declare what an act of war in cyberspace actually constitutes. And I think the reason for that is that all the players at the national level in cyberspace are playing this cat and mouse game, and nobody really wants to go public and define what constitutes an act of war, because the intelligent way to define that would easily draw a line that most of the players have already crossed. Russia, China, North Korea, Iran, and the United States. Foreign espionage in cyberspace is at a all-time high, and it doesn't seem to be abating, and all you have to do is go to the press and the media and pay attention to what the Russians and others have attempted to do, particularly the Russians and the Chinese, on US cyberspace in terms of US national elections, or just in terms of influencing the United States. So that's one big issue. The other big issue that this report found was that the software supply chain infiltration is one of the hugest security holes in this whole thing, and that's how people are getting in, is they're putting viruses and everything else into the software supply chain, and it goes in undetected. So one other risk that I'll mention on 5G, this is highly controversial, whether or not there's a health risk with 5G. 5G is using the spectrum space of 24 to 90 gigahertz, and some people think and claim that that radiation level is such that you don't want to put a 5G cell phone up to your head because you're going to induce some cancer. The people that say, no, it's no threat, point to the fact that it's not ionizing radiation. However, this is something that really needs to be researched, and jury's out on that issue as to whether or not that radiation is a problem. Something as simple as this, as it is a problem, could be a real issue for humans on the planet. So, in addressing cybersecurity, and this is sort of misplaced slide. I forgot to move it to what we're doing, but the Incose vision of 2025 does recognize that cybersecurity is another one of the key skills that a SE has to have. And Incose is really promoting through training and through the improvement of SE skills that cybersecurity be picked up. The Strategies for a system engineer addressing it, you can see there, but continuous threat and system behavior monitoring has got to be designed into systems, management of the access and rights and privileges, and some of the security certificates. That should be something that becomes second nature to SEs and not just system experts in security. And my third grand challenge, which I think is existential, is the aging infrastructure. Unbeknownst to me, the American Society of Civil Engineers every 4 years does a report card on America's infrastructure. And the last report card was 2017. The next one is due out in 2021. In 2017, we got a roaring D+. And it was, there were some improvements in certain categories, but overall the D+ was the same as it was in 2013. So I think the only thing we can say about this is wake up America and ask the question, what are system engineers and what is Incose doing about this problem? There's a lot of critical risk to the US infrastructure, and here's just some examples of reports on infrastructure. And sadly enough, when you do research on it, you find a lot of reports and papers that identify the risk, and you find fewer papers that identify solutions. So we've got an issue there. One of the things you don't think about that is in this report out of DHS is the failing infrastructures of dams. And some of these dams, if they crumble and fail, they're going to make the Jonestown flood look like a picnic. And what's worse is some of the controls for some of these systems that are critical are on the internet, and they're subject to cyber attacks. So they've got all kinds of issues there. The cloud gives a lot of bad actors an entree into our critical infrastructure system in the United States. And the last one is, you can see the redaction on that. It's a released report from the Senate Select Committee on Intelligence, and it's about the Russian intrusion into our networks to mess around with the US election. So the future system environment is here for engineering. And let's say you're an engineer, you're all excited because you got a new job and you're going to design a new system. But there's a problem. That new system has to talk to some old systems. Never fun if you're a system engineer. And they throw some more in. So you go about your task and you say, okay, well, we've got to connect them all, and that's the engineering job, right? Well, it would be 10 years ago. But now you get to put that new system on top of an aging infrastructure. And then somebody gets a brilliant idea that there's some AI out there that can really help this new system, and we should connect that artificial intelligence in. And in fact, that is being done. And management likes it so much that they want the AI to come in and help some of the legacy systems and prop them up, because they don't have the money to replace the legacy systems, so they're going to let the AI come in and do some backstopping. And then the new AI is going to get all connected, and it's going to get put into the legacy system. Then all of a sudden you get this thing out there called 5G, and it lets you connect a whole bunch of different people, different machines, and different robots. And they're actually good robots, so it's no risk. Let's go ahead and put them in. And then you've got more stuff that gets connected by 5G overall. Now, after the 5G is connected to your network and your robots, the good ones are playing, all of a sudden somebody goes south and you get some bad robots and some bad actors that creep in. And then the next thing you know, a bad AI system connects into your overall new system. And from that bad AI system, you launch some more bad stuff and you actually penetrate the new system. And boom, AI or 5G matures from just products and an Internet of Things to a global system and pops over the whole thing, and this is the environment that you're now working in as a system engineer. 5G blankets it all, and all the problems, all the bad actors, and all the connections are in there. So, what do we do? Well, as a start, like any good system engineer, you read, you research, reflect, then you revisit what you've done, you relearn, you redesign, revise, retrofit, you retest it, then you adapt. And if that doesn't work, you repeat it. And this is what all system engineers have really learned to do. And you expand it so that you can incorporate methods from other disciplines. And that's, that's what we're doing, and that's what in the System Engineering Vision for 2025 that's on the Incose website. Have many of you read that? That's a good read. I suggest you go read that. It's a little dated, and I think they're going to update it soon, but in there are principles that are driving the whole organization for the vision for the future. And the future has a particular emphasis for model-based system engineering. That is one of the keys for system engineering in the future. The vision addresses the AI threat generally. It addresses the 5G threat specifically, and it takes a swat at infrastructures in general. I think it could probably do more to try to address the infrastructure issue. When I did research, I found several of our colleagues are already out in front leading with solutions for some of these problems and challenges that they describe in what I think are landmark papers. So the Incose 2025 vision has got a vision for the future state of system engineering, and it's got these 6, I believe there's 6, right? 7. Actually 6, but I've got 7 up there for what Incose is going to do. And the keys there are that it's going to be relevant to a broad range of application domains. Incose is finally getting into the idea that we've got to do cross-discipline interface and assimilation of other ideas from other cross-disciplines and learn to speak the language of other disciplines and learn from them, because that's a better way to actually embrace a customer and learn from a customer and learn from other areas. And that's kind of like an overall theme here, is to have enough language skills and cross-discipline skills that we can have mastery of the next generation of tools, and we can learn from other areas. Ways to address the AI challenge. There was a technical conference right here at GHU, and in there they drew several important conclusions about AI. Some of them are interesting, like for the foreseeable future, teams of humans and machines are going to be more effective working together. So the human in the loop with AI is going to be able to accomplish great things. And there's a lot of work being done on that thing, on that theme. In artificial intelligence, humanity's created our most sophisticated set of tools yet. And it has the potential that we can get further than anything we've imagined in science fiction. And that was kind of the conclusion of this conference. And it was a very progressive and very uplifting conference on where we're going. One thing that was a little bit troubling was the idea that intelligent machines are changing the nature of war. And for that, there's a huge challenge, because it gets down into, again, the idea of a race between robots in a conflict. Now, one of the things I think we need to do is take a hard look at our mathematics. Most of you are very familiar with linear systems theory. If you need a quick refresher on linear systems, I've got it up there in the box. Linear system is homogeneous, it's additive. Together, homogeneity and additivity equals superposition. And there's also shift invariance associated with linear system. So why is a linear system so great? Well, if you remember from your probably sophomore or junior engineering courses in math and engineering, it makes linear systems are simpler, they're easier to describe, they're easier to model, and that's why I think we go to linear mathematics. Makes it possible to completely characterize a system. However, the real world is nonlinear, and nonlinear has messy mathematics, produces outputs that are frequently non-repeatable, which means it's hard to test, and in short, a nonlinear system is everything that a linear system is not. Now, I want to suggest or introduce this man, Mitchell Feigenbaum, to you guys. Is he familiar to the audience? People have heard of him. He is notable, and if you don't know him, you're missing the one point that he's famed for, which is he discovered the universality principle. And it's buried deep within a dynamical system and orders of chaos. Here's what came to be known as a Feigenbaum diagram of an iterated function. Now iterated functions are really, you can think of it as the characteristic equation for a nonlinear system. So once you've got a nonlinear system and you describe it, you iterate it, the output comes back, it's fed back into the input. This is really the way that natural systems work, and increasingly it's becoming the way that all systems work, particularly when they're networked with tons of inputs and asynchronous actors across a network that turn out to be inputs that get produced into your processing system. What Feigenbaum found was this magic number, 4.669, and that's just the ratio of the two areas. So if you see a look at that chaotic system there, it's got one mode in the first region of the constant R. And as you vary R, what happens is you get a bifurcation, and this system will oscillate, but it will oscillate in two distinct modes. And every time you increase the variable, it gets into a region of chaos, and boom, you think it's chaotic, but as you look, you'll see blank regions out there again, and you got regions of stability. Feigenbaum's the guy that figured out that it's not as chaotic as it looks. In fact, all these regions and where they occur all follow that proportionality, and that's his constant. And that is just huge. So what we really need to do is use different mathematics. And what I found from looking at things are, Incose has already got a lot of excellent engineering knowledge built on some of these subjects, particularly in the complexity primer for systems engineers. And if you look at all the different modeling methods that are used, a lot of them are nonlinear. And I'm getting a 5-minute hook. I'm going to need probably about 10 more minutes, but thank you. So the Incose vision is for 2025, addresses influential technological developments, and in the communication technologies, they do take a real stab in the vision at addressing the 5G issue and the 5G problem. And in the human-computer interaction, although it's very general, they do have a vision for how we would engineer up against some of the AI threat. It's not as flushed out as I think it needs to be. So the SE Vision 2025 generally addresses the three threats, and the path forward is really specific about model-based system engineering becoming the primary method that we hang our hat on. In the area of complexity, there's a hierarchy here, and this is addressed. What I want to do is introduce the notion of a wicked problem, which has been around for a long time. Wicked problems are no secret, but they tend to sit more in the area of city planning and architecture. rather than systems engineering. So you see the hierarchy here of any problem set or any system goes from simple to complicated to complex, complex adaptive, and wicked. One of what I think should be mandatory reading for all system engineers, this is a landmark paper, and one of the team members is one of our very own, Dr. John McCarthy, talks about the assessment of complex systems. In the paper, they talk about how difficult it is to do this, why it's still in its infancy, but how you can use a nonlinear method using AI when necessary to engineer a complex system and to model it. And the paper is fantastic, and I think it's pointing the way ahead for really wrestling with the nonlinear problem. In the paper, they identify the different types of complex, and in the paper, they add a complex adaptive system, which is where you actually come in and apply AI to determine the system response and to do something in response to that new input. So it's an early look at humans in partnership with AI producing a system response and dealing with a complex issue or a complex problem. In a wicked system, you've got a system or a problem set where, by definition, not all the inputs are documented or well described. And in some cases, they may not even be known. And that really describes what you have in the 5G network problem. You're gonna be looking at a network that, as you try to model it, you will have no idea of everybody that's hooked up to it, nor what their intent is by hooking up to it. So it's in essence a wicked problem. Here's another paper that I think is really fundamental, foundational for system engineers. This was at the Incose CSIS also. It's something Zane Scott put together, and he talks about, much like, he uses a metaphor of the Tower of Babel and explains how everybody was in a project and then they were reduced to immobility when they were all different languages were thrust upon them, and they found they could no longer communicate because nobody spoke the same language, right? You know, the old Bible story about the Tower of Babel. And it's a very effective metaphor for what the paper talks about, and a couple modeling jobs that system engineers did where they went in and they tried to thrust a SysML model on their customer. The customer knew nothing about the modeling language and wasn't really useful in even helping them extract what the requirements of the system were. And the problem persisted like that until the system engineers got smart enough about learning the modeling system in the language of the customer, and they actually built the system model using 4 different models to extract information. And what they found at the end when they went to harmonize and interface all the models was they had way more information than they ever would have dreamed that they could extract out of the requirements process for building a system. So that became a real principle of design and system engineering, that you've got to be able to use the models and the language of other disciplines and other customer sets when you go about your engineering and your modeling. And it's a great story. I recommend that everybody read that, because it's something that you can really learn from. So how do we address the 5th generation challenge? The SE Vision 2025 does this. It looks and talks about the Internet of Things and the system of systems. And what the vision does there is lay out a path forward for engineering and describing a system of systems and engineering within that system of systems to address a challenge that I think, if you use that process, it will give you a real good start on the 5G problem. SE Vision also talks about collaborative engineering and the automated workflow, data integration and network communications are really critical to the design process and to being able to execute a program. If you can collaborate with other disciplines, that will result in cross-linked engineering workflows, cross-linked engineering data, and cross-linked engineering design methods, and that is the approach that Incose is leading us towards. Here's a look at 5G security, and it came out of some interesting places. It's just one example from several universities in Finland and Sweden, and what they've done is go down through the entire 5G network architecture, identify all the threats, all the vulnerabilities, and they make proposals and suggestions for how you can tighten it up and how you can secure some of those technologies and some of those areas of vulnerability within a 5G. So this is heartening because there are people out there that are working the problem in a big way. They're not US national, but they're in the international community, and Finland and Sweden are some friendly engineers. How do we address the infrastructure challenge? Incose's got a way for that. They start off their vision with saying that what we need to do is look globally and consider all the needs of humans on the planet. And they address the global climate change and our sustainability and natural resources as the two fundamental underlying issues that system engineers designing any system need to be aware of from the environment that they're designing within. The globalization issue and the population growth all impact infrastructure, and there are considerations that need to be taken into account when you design a system. There aren't real good strategies identified in the vision for how we really wrestle with the infrastructure problem, and I think that's one of the areas where we could get better. The American Society of Civil Engineers, they've got a paper and they've got a policy about the grand challenge, and this is how they're addressing it. However, their grand challenge is not really strongly supported by anything that the government is doing. And this is something that really needs to be identified as a crisis level. Then we've got another thing for security infrastructure is the CSIS. It's the Crypto Security Infrastructure Security Agency, which is really new. This was established by President Trump November 2018, so it's a little older than just a year. I think it sort of looks like a combination of what the old DISA, Defense Information Security Agency, used to be, and some pieces of cybercom were trying to be all established in this agency. And they've got a website and they seem like they're doing good things. But again, funding is really what the problem is behind this. It's going to cost billions to fix the infrastructure, and the budget isn't there right now. Now, just a couple areas where you can get smart in a wicked problem. And these are very, very dated papers, but they're foundational papers out of city planners, and they have got some great ideas in them for system engineers. Horst Rittel is one of the well-known characters in the whole area of city planning and operations research. And he talks about all planning problems are wicked problems because you're in the middle of a problem, you don't know what resources you're going to get, and you don't know what all the inputs are. So a wicked problem has a lot different characteristics, and system engineers typically don't think of a system problem as a wicked problem, but I I will hypothesize that increasingly in the future, more and more of our system problems are wicked problems, and they're going to stay wicked problems. And they do fit the definition. Number two, wicked problems have no stopping rule. That is, that's really, really applicable, because whenever you're designing to a wicked problem, how do you know when to stop? How do you know what the criteria is that you've satisfied to tell yourself that you're done? And in a wicked problem, the answer is you don't. Each wicked problem is essentially unique. You get into it. It's also very risky because it's got social consequences associated with it. It's basically one-shot engineering. You try a solution, and until you actually apply it, you don't even know if it works. It's very, very hard to model. It's very, very hard to even simulate. So that's one of the natures of it. And a planner in a wicked problem has no margin for being wrong. Unlike a scientist that can make a hypothesis and test it, the designer of a solution for a wicked problem doesn't really have a margin for error. One other paper, and this goes back to '57, but it's kind of humorous, but it's actually deals in earnest with wicked problems and how you approach them in the science of muddling through. And what the paper basically says is you dive into the center and you work the problem locally, and you work outward from the center, making as much progress as you can and measuring the progress up against the problem as you go. And this is not all that different now from iterative design in software, or in any kind of problem where you've got to hand out limited resources to more people with their hand out than there are resources for, and you've got to come up with some criteria as to whose problem you attempt to solve first, particularly in social problems, is where this applies. So I want to leave you with a couple thought provokers. And does Incose boundary definition of a system need to be amended? The Incose engineered definition does have a pretty identified boundary. And as you can see, some of these system challenges I've talked about tonight don't have real clear boundaries. Does a recognition of underlying order in a random problem space, will that allow the possibility of even limited prediction and or control? Well, it could if we use nonlinear science to address the problem. What about the idea of building a control system for a superintelligence? Think about that. Do you think we have a chance? And another thought provoker, will the ubiquity of fifth generation comms from all kinds of devices and systems, will that overwhelm our ability to effectively respond to anything in this digital world? Particularly if the digital world is blanketed by just an unending series of queries, requests, and even attacks. And then for the infrastructure problem, food for thought, who really thinks it's their job to solve that problem? Is it the government, the American people, or is it some responsible system engineer? Here are some of my conclusions, and I've addressed many of them for the artificial intelligence and 5G and aging infrastructure, but I want to leave you with these takeaways. Not all engineering problems are going to be linear, self-contained, or well-bounded. And that is to say that we're very solidly in the era of nonlinear, unbounded engineering problems, and it really is challenging our ability to solve these problems using the older methods that we've all grown up with. The current adaptive model-based system engineering, I think, is the correct approach for addressing the complexity and the complicatedness of systems, and also delivering a quality solution. And the last one is key. System engineers are going to need to learn new methods and keep learning new methods, which is no It's no great revelation to any of you. Those of you with system engineering careers I know have always been challenged by continuing education and a need to continue it throughout your career. So with that, I'd like to thank you all for coming and listening, and I'll open it up to questions for about okay, time for a couple questions.
Hi. So first of all, I want to thank you for this presentation. It was very thought-provoking into putting these new challenges in context. However, as a systems engineer, a young systems engineer, I would argue that most of these challenges are actually opportunities to make to advance systems engineering as a profession rather than as a limiting factor or as a threat towards the future of it. To explain this, could you go back to slide 11 of your presentation, please?
Okay. If the control room can type in 11 in a return, we'll get right there fast. Won't be long. Is that it?
11. No, that's not 11. Okay. So I think it's really interesting that you point here some Pinker quote, which I am not familiar with. However, I believe that Pinker's new book on Enlightenment Now, he provides more of a stance that the advances of technology, we should not see them as a threat and pretty much be bullish towards this progress of implementing specifically AI and the Internet of Things. Furthermore, if you go back to slide 7, so yeah, it's in here. This is where I had the idea that artificial intelligence is really an opportunity for systems engineers. So, for example, the current implementation of model-based systems engineering does not use artificial intelligence per se, but some of the methods or mathematical methods that are used in artificial intelligence systems to solve problems that may be considered out of scope. And I think that the approach of seeing it as a potential threat is maybe a little bit misguided, which I will also go back to slide 5. Something that I was a little bit uncomfortable is with Clifford Stoll's quote. So I'm very familiar with not very familiar, but fairly familiar with Clifford Stoll and his work. And I believe that this quote was taken out of context in the sense that I don't think that he was predicting that the newspaper will not be replaced by something digital, but pretty much Clifford's main work is into teaching. And I believe that there are some things that artificial intelligence will not be able to replace us. And one of them, as presented by the body of work of Clifford, is teaching. You cannot substitute a great teacher at any time in the development of a human being.
Thank you for your comments.
We just need to wrap it up.
So
We probably should have gotten you up there. You have a lot of good points, and unfortunately you can't answer right away.
Right. Well, thank you. And for Clifford, perhaps I made a joke at his expense. But, it possibly is taken out of context. I did try to say that, a lot of what he was concerned about actually was true. But the, on base, what he said was a little bit humorous as to how things have slid off.
very humorous guy.
All right, so let's get our book.
About the book, you guys got your...
Okay, we have a...
Ready?
What of the books are the ones he actually talked about? Superintelligence.
Superintelligence by Nick Bostrom.